Okay, so this is the rest, chapter 11 in its entirety. As always, please pause the video if you wanna, when I suggest that you do, so you can practice problems on your own before looking at the answers. And please have these notes printed out, the blank ones, so you can follow along and fill in blanks. Last Thursday, on the 7th, we started chapter 11. We brainstormed what we already knew about gases, and we used that information and applied it to learning more about ideal gases specifically. So these are instances where gases are behaving more like noble gases, where the particles have no volume and the particles themselves do not interact. They don't have intermolecular forces. Shocking. I know, because we talked so much about them. But in this case, when we're talking about ideal gases specifically, we're not worrying about intermolecular forces. If you go on to Chem 120, you will learn about a different case where they're not behaving in an ideal manner. It's a whole other set of rules, but for right now, you don't have to worry about that. I do want you to know the gas measurements. So volume, which you have seen, is in liters or milliliters. When you're using the ideal gas law, you always want to convert to liters. Pressure, we introduced on the next page. Temperature is always in Kelvin for the gas law itself. So if you're given Celsius, you need to remember the conversion. And then moles are always moles. In this case, for the ideal gas equation, it is abbreviated as the letter, or the variable is the letter N. We talked about pressure. Pressure is defined as a force per area. Talked about the units. We are going to use the units of atmospheres, which are equal to 760 millimeters of mercury. Again, this is a conversion, so it's an exact number, and there are no significant figures from these values. Oops. We said pressure of an ideal gas is caused by collisions with the container itself. So that force per area comes from the collisions of the container. Pressure outside the container and the volume, as pressure goes down, volume increases. As pressure goes up, volume decreases. The little fish arrow means relationship, and in this case, pressure and volume are inversely proportional. As one goes up, the other goes down, so they're opposites of each other. Pressure and temperature we found were directly proportional to each other. As pressure increases, temperature should increase. As temperature increases, pressure should increase, or they both decrease. We answered some questions. What happens to the number of collisions of gas molecules experienced in the following scenarios? What happens if you decrease the volume? If you make the space smaller, you should increase the number of collisions. What happens if you increase the volume? If you make the space bigger, the number of collisions on the container should decrease. So how does that correlate to pressure? Well, pressure should increase because in scenario 1, if you are decreasing the volume, the pressure should increase. We just said volume and pressure are inversely proportional. So if I decrease the volume, the pressure should increase. If I increase the volume, the pressure should decrease, go down. From this, we figured out that pressure and collisions are directly proportional. So in scenario 1, volume decreased, but number of collisions increased and pressure increased. They were going the same direction between pressure and collisions. Scenario 2, the volume increases, the number of collisions decreased, and the pressure decreased. Well, what's colliding? Well, the gas particles are colliding, and we define the number of things as a mole. 6.022 times 10 to the negative 10 to the positive 23 somethings, in this case gas molecules. Those are the things colliding, and from this we figured out that pressure is directly related to moles. It's directly proportional. As the pressure increases, the moles of gas would also increase. We combine those three relationships. Pressure inversely related to volume, 1 over volume, pressure directly proportional to temperature, and pressure directly proportional to the moles of the gas. I just took pressure and related it to everything at once, so temperature and moles have to be on top because they're directly proportional, and then I divide those, or I put the volume on the denominator because it is inversely proportional to pressure. This is the basis for the ideal gas law. Pressure equals, so the relationship is that pressure is equal to temperature times the moles divided by volume, and then we have this R constant, which just takes care of all of the units. If I divide by volume on both, or multiply by volume, on both sides, this is typically the way you'll see the ideal gas law written. Pressure times volume equals moles times R, the gas constant, times temperature. You can rearrange this however you need to, depending on what you're solving for. We then solved for R itself, and we figured out that given this context, this specific context, that 1 mole of any ideal gas has a volume of 22.4 liters at 0 degrees Celsius and 1 atm. We called 0 degrees Celsius and 1 atm standard temperature and pressure. We did some conversions to get the right units, plugged it into the ideal gas equation, and figured out that R should be 0.0821 atoms, liters per mole Kelvin. You must write all these units every time you're doing these calculations. You will get marked off if you are not writing your units. It's going to get very confusing if you don't write your units. And again, if you're going on to Chem 120, it is important that you understand where R comes from, and remembering this little background can also set you up for a shortcut as you go further into chemistry with gases. I told you that the R will be given to you on a reference sheet, but again, if you're going on to Chem 120, if you have questions on how to calculate it, let me know. So now I'm going to show you the 5 types of problems you're going to come across using the ideal gas equation. I'm going to show you an example of each one, and I'm also going to give you time to go through an example on your own. The first type is single variable. Basically, I'm going to give you everything except for one of the variables in the equation, and expect you to figure that out. So the steps of any problem that you're given with with the gas equation, you're going to want to rearrange the gas equation for whatever you're looking for, your unknown, and then you're going to want to check that your units that you are given to work with actually match up with the R value. And lastly, once your units match up and you know exactly what variable goes where, then you can just substitute what you have and solve for what you don't know. Right. All right. Working now. No. Alright, hold on. I'm gonna have to post 2 videos.